We'll start in 1 minute. Okay, today we'll do a few more problems in section 10, and then we'll do some stuff from section 11. So we didn't do this one yet. This use the binomial series to find the series expansion of 1 plus x squared to the 1/3. So I will do that on a different piece of paper. So I've written down the binomial series definition. So if k is any real number and the absolute value of x is less than 1, then the binomial 1 plus x to the k is equal to the series, the coefficients. These are called the binomial coefficients. K choose n and then x to the n. K choose n is defined as k times k minus 1 and so on times k minus n plus 1 divided by n factorial. So we'll apply that to this particular binomial raised to the 1/3. So we can write the sigma notation right off the bat, but we'll actually write out the terms here in a minute. So the sum from n equals 0 to infinity, the value of k is 1/3. 1/3 choose n, and we're going to have x to the second to the n, or we can just write x to the 2n. Okay, so let's start the expansion. The first coefficient, 1/3 choose 0 times x to the 0 plus 1/3 choose 1 times x to the 2 times 1. Maybe I should write x squared to the first. And then 1/3 choose 2 times x squared to the second, and so on. We'll write out a couple more terms. 1/3 choose 3 times x squared to the third, and then 1/3 choose 4 times x squared to the fourth, and so on. Okay, 1/3 choose 0 is just 1, and x to the 0 is 1. So 1 and then plus 1/3 choose 1, that's 1/3 divided by 1 factorial times x to the second. And then what's 1/3 choose 2? Yeah, 1/3 times negative 2/3 divided by 2 factorial. So all we did was subtract 1 from 1/3 to get negative 2/3, and then times x to the 4th. And then 1/3 choose 3. It's 1/3 times negative 2/3 times negative 5/3 divided by 3 factorial times x to the 6th. And we'll be able to squeeze in one more, it looks like. So 1/3 choose 4. 1/3 times negative 2/3 times negative 5/3 times negative 8/3 divided by 4 factorial times x to the 8th, and so on. Okay, so let's just do some of the arithmetic. We get 1 plus 1/3 times x to the 2nd. And what's the next term?
Negative 2/3 over 2 factorial.
Yeah, the coefficient is going to be negative, so we write minus. So 1/3 times, well, we've taken care of the minus, so 1/3 times 2/3 is 2/9, and then 2/9 divided by 2 is 1/9. So minus 1/9 x to the 4th. Okay, then the next term, 1/3 times negative 2/3 times negative 5/3 divided by 3 times 2. So we get 10/27 divided by 6. So that's, yeah, it's going to be 5 divided by 81, x to the 6th. Is that what you got? So yeah, 10/27 divided by 2 times 3. So 10 divided by 2 is 5, and 3 times 3 to the 3rd is 81. So plus 5 over 81, 8x to the 6th. And then the next one has to be subtraction because the coefficient is negative. So this one, minus minus 80 over 81 over 4 factorial. So let's do the arithmetic on the side here. So let's see. 80 over 81 divided by 4 factorial. That's, so we're going to divide by 4 times 3 times 2 is 24. So 8 goes into 80 10 times and into 24 3 times. So it looks like we get minus 10 over 243 times x to the 8th, and so on. So for this one, we won't bother trying to write it in sigma notation. If you can write out the first few terms in a case like this, that's good enough. Okay, the next problem from section 1110 that we just got started on last time. Find the Taylor series for f of x centered at the given value of a. So f of x is the natural log of x, and a is 2. So let's find the first few derivatives. So the first derivative is 1 over x, and then evaluate that at 2, we get 1/2. The second derivative is negative 1 over x squared. And then the second derivative evaluated at 2 is negative 1/4. The third derivative, this one's positive 2 over x to the third. Evaluate the third derivative at 2, we get 2 over 8, which is just 1/4. Just a couple more. The fourth derivative. So the fourth derivative is negative 2 times 3 over x to the fourth. Evaluate the fourth derivative at 2. So we get negative 3/8. That's what I got. Okay, one more. The fifth derivative. This will be positive 2 times 3 times 4 over x to the fifth. And then the fifth derivative evaluated at 2. So the denominator is 32, but we have 2 times 4 or 8. So this reduces to positive 3/4, I think. Okay, so we can begin writing the Taylor series. So we need f of 2. F of 2 is just the natural log of 2. Okay, so the Taylor series, natural log of 2 over 0 factorial So I'll go into some detail just to make sure we cover the bases. The first term, natural log of 2 over 0 factorial times x minus 2 to the 0. And then plus the first derivative evaluated at 2, so 1/2 divided by 1 factorial times x minus 2 to the first. And then the next term, oops, well, we'll fix it later, I guess. So the second derivative evaluated at 2 is negative 1/4. So negative 1/4 divided by 2 factorial times x minus 2 to the second. Let's squeeze in one more up here. So the next term, the third derivative evaluated at 2 is 1/4 divided by 3 factorial times x minus 2 to the third. Okay, so we get 1 plus, sorry, we get the natural log of 2 plus 1/2 times x minus 2 to the first. And then negative 1/4 divided by 2 is negative 1/8. So we write minus 1/8 times x minus 2 to the second. And 1/4 divided by 3 factorial is 1/24. So plus 1/24 times x minus 2 to the third. And so on. So we got 4 terms. You know how to figure out a couple more if you have to. Okay, the next one, f of x equals e to the 2x, a is equal to 3. So let's find the first few terms of the Taylor series. Okay, well, if f of x is e to the 2x, then f of 3 is e to the 6th. And then the first derivative is 2 times e to the 2x. Evaluate the first derivative at 3. We get 2 times e to the 6th. The second derivative is 2 times 2. I'll write it as 2 to the second times e to the 2x. And then evaluate the second derivative at 3. We get 2 to the second times e to the 6th. So just a couple more. The third derivative is 2 to the third times e to the 2x. The third derivative evaluated at 3 is 2 to the third times e to the 6th. The fourth derivative is 2 to the 4th times e to the 2x. Evaluate the fourth derivative at 3. We get 2 to the 4th times e to the 6th. Okay, so the Taylor series expansion, f of 3 divided by 0 factorial. So e to the 6th divided by 0 factorial plus 2 times e to the 6th over 1 factorial times x, the quantity x minus 3 to the first. Okay, then plus 2 to the second times e to the 6th over 2 factorial times x minus 3 to the second. And so on. 2 to the third times e to the 6th divided by 3 factorial times x minus 3 to the third, and then just one more, plus 2 to the third times e to the 6th over 4 factorial times x minus 3 to the 4th, and so on. So this one looks pretty simple to get into the sigma notation, so why don't we do that? Starting at n equals 0 to infinity. So what do we get? We get 2 to the n times e to the 6th over n factorial times x minus 3 to the n, it looks like. Okay, the next page. Use the Maclaurin series for e to the x to get a Maclaurin series for e to the negative x squared. So remember what the Maclaurin series is for e to the x. It's 1 plus x to the second over 2 factorial, and so on, plus x to the third over 3 factorial. Okay, so e to the negative x squared we just replace every x in the expansion for e to the x with negative x squared. So we get 1 plus negative x squared to the first plus negative x squared to the second over 2 factorial, and so on. Okay, we'll simplify a little bit more. So we get 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial. And then plus x to the 8th over 4 factorial minus x to the 10th over 5 factorial, and so on. Okay, so in the next part, we evaluate the indefinite integral of e to the negative x squared and write it as an infinite series. So all we do here is use this series up here and find the antiderivatives of those terms. Okay, so we get x minus x to the 3rd over 3 plus x to the 5th over 2 factorial times 5 minus x to the 7th over 3 factorial times 7 plus x to the 9th over 4 factorial times 9, and then minus x to the 11th over 5 factorial times 11, and so on. Is that what you got? Okay, so then in the bottom part, we evaluate the definite integral of e to the negative x squared dx from 0 to 1. So I guess I should rewrite all of that. You don't really want me to do that, do you? So we can can, if we were to evaluate this definite integral, we would evaluate this expression from 0 to 1. And when x is 0, everything is 0. And so we can write what this is equal to by replacing every x with 1. So we'll get 1 minus 1/3 plus 1 over 2 factorial times 5 is 1/10. And then minus 1 over 42, 3 factorial times 7. And then plus, let's see, that's 4 factorial times 9 is 216. And then minus 1 over, let's see, 5 factorial is 120, right? Times 11 is 1320. So you can check my arithmetic on that. Okay, but with that many terms, it turns out that this is a pretty good approximation of what that definite integral is. And you might remember earlier this semester, according to the textbook, there isn't a known antiderivative of e to the negative x squared as a enclosed form. But since it does have a Maclaurin series, then that Maclaurin series can be used to evaluate definite integrals involving e to the negative x squared, e to the negative x squared. Okay, let's start section 11. Well, since we're running out of time this semester, we won't go into extreme depth in this section 11. But as we have seen, many functions are equal to the sums of their Taylor and Maclaurin series. Therefore, those functions can be approximated by their Taylor polynomials. And according to the author of the textbook, Taylor polynomials are used in computer science because polynomial functions are the simplest of functions. And Taylor polynomials are also used in physics and engineering. And this in quotes from the textbook, Taylor polynomials are used in theory of relativity, optics, black body radiation, electric dipoles, the velocity of water waves, and building highways across a desert. Okay, so if f of x, we've seen this before, if f of x is equal to the sum of its Taylor series at A, then f of x is equal to this Taylor series. The coefficients are the nth derivative of f evaluated at A divided by n factorial. And the binomials are x minus a to the n. And this can be approximated by the nth degree Taylor polynomial, t sub n of x. And t sub n of x is just a partial sum of the Taylor series. So if you expand it out, it looks like this. We've seen this before. T sub n of x is the nth degree Taylor polynomial of f at A, also known as the nth partial sum of the Taylor series of f at A. Okay, so to reiterate this idea, not hard to understand, but since f of x is equal to the limit of the Taylor polynomials, it follows that the function f of x can be approximated by its Taylor polynomials. The larger the n, the better the approximation. Okay, so here's a little exercise. I'll give you a couple of minutes to think about this. Maybe it will only take you a few seconds. Suppose a function f is equal to the sum of its Taylor series at a. Find the first degree Taylor polynomial of f at a, and then explain where you have seen it before and describe what its utility is or what it's used for. So I'll give you a few seconds to work out the degree 1 Taylor polynomial in symbols. More specifically, the first degree Taylor polynomial of the function f at a. So online, if you come up with a first degree Taylor polynomial of f at a, if you recognize it, just type in a few words to indicate what it's used for, or what it is and what it's used for. You're making headway? Anybody? Okay, we have a formula for the nth degree Taylor polynomial. So let's just write the formula for the first degree. So t sub 1 of x is the sum starting at I equals 0 going up to 1 of the terms are the ith derivative evaluated at a divided by I factorial times x minus a to the power I. So there's only two terms in this. When I is 0, we just get f of a. And then we add that to the first derivative of f evaluated at a. Times the binomial x minus a to the first. So what is that?
Is it slope-intercept form? Slope-intercept form?
It's an equation of a straight line Which line?
R equals mx plus b.
It can be written in the form y equals mx plus b. Yeah, it's a straight line. If we distribute multiplication by f prime of a, I'll just use f prime instead of this other notation. So this first degree Taylor polynomial is f of a plus f prime of a times x minus f prime of a times a. So maybe it would be more familiar if you replace t sub 1 of x with y. So we get y equals f of a. I'm going to rewrite that in factored form, plus f prime of a times x minus a. Okay, well, this is the tangent line. It's a line that's tangent to the graph of the function f at a particular point. So t sub 1 of x is the line tangent to the graph of f. Okay, so let's move on to the next example. So on this one, let f of x be equal to the natural log of x. We'll find the nth degree Taylor polynomial of f at a equals 1. And then we'll use the 6th degree Taylor polynomial of f at a equals 1 to approximate the natural log of 1.5. So let's just start by finding 6 derivatives of the natural log of x, and then evaluate each one of those at a equals 1. Well, the natural log of 1 is just 0. The first derivative of f is 1 over x. Evaluate the first derivative at 1, we get 1 over 1, or 1. The second derivative, the derivative of 1 over x is negative 1 over x squared. And so the second derivative evaluated at 1 is negative 1. I know this is probably tedious, but so the third derivative is going to be positive 2 over x to the third. And the third derivative evaluated at 1 is positive 2. Fourth derivative is negative 2 times 3. We'll just write negative 6 over x to the fourth. Evaluate the fourth derivative at 1, we get negative 6. A couple more derivatives. The fifth derivative, this one is going to be positive 24 over x to the fifth. Evaluate the fifth derivative at 1, we get positive 24. And then the sixth derivative, this one is negative 120 over x to the sixth. Evaluate the sixth derivative at 1, we get negative 120. Okay, so let's write down the degree 6 Taylor polynomial at a equals 1. So t sub 6 of x. Well, f of 1 is 0. I'll go ahead and write 0 just to remind us that the first term is 0. And then the next term, the first derivative evaluated at 1 is 1. So 1 over 1 factorial times the binomial x minus 1 to the first, and so on. The second derivative evaluated at 1 is negative 1, so we get plus negative 1 over 2 factorial times x minus 2 to the second. Then the next term plus 2 over 3 factorial times x minus 2 to the third. And the fourth derivative is negative, so let's write minus 6 over 4 factorial times x minus 2 to the fourth. Then plus 24 over 5 factorial times, oh, I see my mistake. Yeah, throw in the towel next time. This should not be x minus 2. The value of a is 1, so that's x minus 1 squared, x minus 1 to the third, x minus 1 to the fourth. Now this one, x minus 1 to the fifth, and then minus 120 over 6 factorial times x minus 1 to the sixth. Okay, let's simplify a little bit. So we get x minus 1 to the first minus 1/2 times x minus 1 to the second. And then plus 2 divided by 3 factorial is 1/3 times x minus 1 to the third. And then minus 6 divided by 4 factorial is 1/4. And then times x minus 1 to the fourth. 24 factorial divided, 24 divided by 5 factorial is 1/5. And then finally, minus 120 divided by 6 factorial is minus 1/6 times x minus 1 to the sixth. Okay, you can see what the nth degree Taylor polynomial is going to look like. But what we're going to do is we're going to use this sixth degree Taylor polynomial to approximate the natural log of 1.5. So first, the natural log of x is approximately equal to the degree 6 Taylor polynomial. And so we'll use that to approximate the natural log of 1.5. Okay, so down here, let's do that. This won't be too bad. Replace every x with 1.5. So first, 1.5 minus 1 is 0.5. And then we can write 0.5 squared over 2. And then plus 0.5 to the third over 3. And then minus 0.5 to the fourth over 4. And then plus 0.5 to the fifth over 5. And lastly, minus 0.5 to the sixth over 6. So I didn't bring a calculator, but you can use your calculator to compare this approximation with what your calculator gives you for the natural log of 1.5, and they are pretty close. Okay, the next thing, we'll just get started on this part. So suppose the function f is equal to its Taylor series at a, and the Taylor polynomial of f at a is going to be used to approximate f within a specified threshold of accuracy. So how is it determined how accurate a particular Taylor polynomial is in its approximation of f at a? So I need to take this s out of that. So how is it going to be determined how accurate a Taylor polynomial is when it's used to approximate a function f? There are just more than one way to do it, but according to the textbook author, the Taylor's inequality will always be able to be used. So here's a reminder of the Taylor's inequality. So recall that f of x is equal to the nth degree Taylor polynomial plus the remainder, capital R sub n of x. And so the absolute value of R sub n of x is equal to the absolute value of f of x minus the degree n Taylor polynomial. And Taylor's inequality states that if the absolute value of the n plus first derivative of f is less than or equal to capital M for values of x that satisfy this inequality, the absolute value of x minus a is less than or equal to d, then the remainder, the absolute value of the remainder is less than or equal to m divided by n plus 1 factorial times x minus the absolute value of x minus a to the n plus 1 for values of x that are in the specified interval. Okay, we won't have time to do this today, but this exercise. You might try it out and see. Here we just want to find the degree 3 Taylor polynomial of f of x equals x to the 2/3 at a equals 1. And then see if you can use Taylor's inequality to estimate how accurate that degree 3 Taylor polynomial is. But we're about out of time, so I think on Friday we'll start reviewing for the final, and then on Monday and Tuesday of next week we will continue reviewing for the final.